Hello everyone, I hope that you are fine. Welcome to another session of Robotics Lab. Today we shall try to implement artificial potential fields or virtual potential fields. We shall use MATLAB for this purpose. Just a quick review what is artificial potential fields and why it is important for path planning. So this is another method for path planning or the robotics, and so what we do, this is our configuration space or the environment we have, and then let's say here we have obstacle here. This is start point and this is our goal location. And now the robot want to move from this location to the goal location. So as we learned in the lecture that we assign this, we made a model. We model this field as a virtual field, and we assign the goal location as the zero potential, and the obstacles we assign the highest repulsive potential, and the goal has the lowest attractive potential. So we model it using a quadratic function in which we have, so we model it like this, a quadratic function in which the goal is located somewhere here and it has a lowest potential, and so whenever your robot is anywhere here, it will be attracted by the attracted toward the goal, and finally when it reaches the goal, then it will stop there. So for more details you should consult the lecture. And then we also said that there is a force toward goal which is an attractive force, but also meanwhile there is a repulsive force from the obstacle that repel the object or robot away from it. So the net force acting on the robot is the sum of the attractive force, or we can say FA, and repulsive force FR. So the robot will move toward the goal, and whenever it feels the repulsive force, it stay away from it and then finally reach the destination. So this is a quick review, and now let's see how can we implement this in MATLAB. So again we shall download code from here. So this website, you have to go there and download this code. You don't need to log in here, just click the download zip and then the code will be there. And you have to download again another code here. This is a different code developed by someone else, and so this is also related to artificial potential field for mobile robots. And then we have a MATLAB code here for robotic arm, and this is also it also uses virtual potential fields to avoid obstacles, and you have to log in there and then just press download. So I have already downloaded all these three codes and they are available here. And so what you need to do is to first look at this code. What's an advantage of this code is this is not complete actually. This will there is some function in this code that is missing. So we shall use this code to visualize the attractive potential and the repulsive potential and the sum of these two potentials. Okay. And then we shall go to this code, this second code that we downloaded, and in this code we this is for actually the potential field based navigation of a mobile robot, and here you will see the mobile robot avoiding the obstacles. And then finally we shall try to run this code and see that how robotic arm can avoid obstacles and reach the goal using potential fields. So first we try to run this code. This is the first one that we have downloaded from here from this website. And so what you need to do is you need to first see that it has a number of rows, number of columns. This is the size of your matrix or the configuration space. Then there's a function to generate some obstacles, and there are 1, 2, 3, 4 obstacles are being generated here. And then there is calculation of distances, and then there's a function to display the repulsive potential, and then we compute the attractive force. And in the next step it display 2D configuration space. It shows you the configuration space where the obstacles and your goal and the start point is located here. And then it calculates the total force here by combining the attractive and repulsive forces, and it gets the total force. And this force will also be displayed as a mesh or as a graph. So this function is missing, so that's why this code is useful till here, where we only use it to display some plots. So let's run it and see how it works, how it looks like. So as you can see clearly, there is an error here. This function is missing. So what we can do, we can try to just, so this is our configuration space, and you can see there are 1, 2, 3, 4 obstacles. 2 of them are circular, and then we have rectangular obstacles, and the size of your configuration space is 400 by 600. And so here is your goal located, the red point. So now how we can model it using the virtual potential. So it should look like the goal should have the lowest potential and obstacle should have a highest potential. So first let's see only how we can model the attractive potential for the goal. So this is the attractive potential for the goal. If you can see that it is highest at this location 400, and because here your start point will be located, and it is lowest at x-axis 400. Sorry, this is the z-axis, and this is the y-axis, and this is x-axis here. So x-axis was from 0 to 600, y-axis was from 0 to 400, and z-axis is 0 to 400. So you can see that the start location is located at 400 and 0, and it has the highest potential. So the magnitude of potential is on z-axis. It has the highest value upon the z-axis at the start location, and it has this potential. So this is a 2D mesh, you can say, which is being shown in a 3D environment. So you can say this is some kind of sheet that is that has different levels, and you can see the minimum, it has a minima at somewhere here. You can see this point here, it has a minimum value near here somewhere, yeah, where the goal is located. And this is again a quadratic function, but it is in 2 dimensions. So yeah, that's why you see a total of 3-dimensional figure here. So this is attractive potential. So whenever you imagine this is as a sheet, and if you put a ball here at this location, it will start moving downward, okay, and when it reaches here, then it will stop. So this will be your goal. So yeah, now we see this was our attractive potential. Now we see the repulsive potential we have here because of the obstacles. So this is the repulsive potential. As you can see, we have 4 obstacles here, and obstacles are given the value of high potential, repulsive potential. So this is here the x-axis here, and this is the y-axis, and you can see all obstacles, they have almost same repulsive potential, and the value is 200, the magnitude of the repulsive potential. So this is in 2D, this is how it looks like. So these two are circular obstacles, and these are the rectangular obstacles, and when you see their potential, so it comes like this. So what happens when you put a ball here near this obstacle? What it will do, it will start moving downwards away from the obstacles. But finally the ball will move somewhere here or maybe here because of the obstacle, but it will never ever it can stay here on the boundaries of obstacle. Okay, so now we studied in the lecture that the total force or the total potential is the sum of attractive and repulsive potential. So sum of this attractive potential and repulsive potential. So this is how in 2D it looks like. This is the attractive potential we have. So here the highest value, our starting point, and here we have somewhere the goal point here, the lowest value. And now when we add the repulsive and attractive potential, we get this here. So you can see that now this was our configuration space, and we modeled our configuration space or our environment as a virtual potential or as an artificial potential. So what happens here is that we assigned the obstacles an repulsive potential and the goal attractive potential. And when we see the net result, you see that if you place a ball somewhere here, so this is your start location, let's say here, okay, when you put a ball here, it will start moving downward. Let's say there's a gravitational field here, the ball will start moving downward, moving here, and finally it will reach here to the goal location, okay, which is the global minima. That's what we wanted. So that's how we model the environment using the virtual potential field. And there are some cases when ball moves here and it gets stuck here to the local minima, and the ball will not move. So this is one of the disadvantages of using the artificial potential fields. Okay, so now this visualization of the potential field is clear. So now if you place a robot here somewhere, the robot will start moving in this direction until it reaches the goal location. So you see that we don't need to make a grid here or make any tree, just need to calculate the virtual potential, and which will automatically lead the robot to the goal. And this thing is very quick, and that's why artificial potential field method can be used in real time or in reactive control. But unfortunately this code is not complete. We cannot calculate the path, so we close it here. And to calculate our path, we try this second code, this one that we have downloaded from this website. Yeah, this is just need to click here and then download zip file, and then you just need to import it in your MATLAB, and then just try to understand what's going on here. So this is again for artificial potential fields for the path planning and navigation of a mobile robot. So in this you can see that the robot has a coordinate. This is the start position, and then we have defined two obstacles, 6, 7 at location 6, 7 and 6, 5. And then we have goal coordinates here. The robot is equipped with a sensor that has a range 2. You can change it by yourself manually. So we have a step size which defines how many steps or what is the step size when you move towards the goal. And then we have obstacle here, goal here, target alpha mu 470, 0.5, 0.5. This one I'm not sure what this is doing here. So now let's move quickly, and first it will plot here your axis, the size of your workspace or the configuration space, and then it will create a target here. After that, in the next step, create a purple transparent circular obstacle. So this is how you create the obstacle for visual display. So it uses this command, fill command here, which will show some kind of maybe circular obstacle, and it's using two obstacles in this plot. And then in the next step, there's a code for creation of a robot. It's some kind of symbolic robot, okay, that looks like a circle maybe. And then there's a code for calculation of your virtual potential. So it calculates your obstacle repulsive potential from obstacle 1, then repulsive potential from obstacle 2, and then the attractive potential from your goal. And finally it will add both of these potentials to create a total potential here. And then there is a function to calculate the distance to the goal, and then we have some artificial points that leads toward the goal step by step. And then there's a cost calculation and error calculation, and yeah, so finally there is some code for the to plot these results and outputs here. and not all things are necessary. So now just try to run this here code. And have you seen that these two purple, these were obstacles, and this was our robot, and every step it's moving toward the goal. So this was the first location, and in the second step this was a green circle, in the third step there's a purple circle, and then so on. It keeps moving till the target achieved. So this was your start location of the robot, and this is the target location. Now let's try to make some changes here. What we can change is, let's try to decrease the range of the sensor and make it 1. And what else can we change here? Okay, first just change the sensor of the robot. So this robot is equipped with some kind of sensor, ultrasonic sensor maybe, that can detect the distance from the obstacles. So we have defined the range of 1, and so the range, let's make it 4. Let's see what happens. Okay, so when we increase the range, so the size of this circle increases. So it means that it can detect obstacle within this range here. So let's make it 2 again, and let's try to decrease the step size. So step size is 0.4, and now let's try to make it 0.01, and let's see what is. So as you can see that now it will take small steps, and it will try to reach, this is the goal point here, these are the obstacles. So it's just trying to avoid the obstacles, and because of the repulsive force from the obstacles, it's staying away from the obstacles, and also meanwhile it's moving toward the goal also. As soon as the repulsive potential will be less, you will see that it will go straight toward the goal. But still it is under the influence of the repulsive potential from the obstacles. So yeah, so almost it reached the goal, and took so many steps, maybe a couple of hundred maybe. So what else can we change here? We can okay, this may be the obstacle size. Yeah, because this was the origin of the obstacle, and this is the size of the obstacle. So let's make it, instead of 4, make it 6, and here make it 0.1. Let's see the results. So of course now it was faster. I don't see any change in obstacle. Let's try it one more time. Put it here, 4 and 6. Okay. Yeah. So this was just for to visualize how navigation or path planning is done using the artificial potential fields, and how the mobile robots can reach toward the goal location using this method. And this is very quick, fast method that can be used in real time. Now we shall see a code that is used for robotic arms. It uses artificial potential fields for obstacle avoidance and for finding or reaching towards the goal location. So you can download this code from here, from MATLAB website. So here, what's happening here is that it has first it says that you can make some choices here. By default, choice is 1, the value is 1, but you can also make this value from 1 to 5. It means that for each value of choice, you will get a different mode. For example, if you select choice is equal to 1, then a function for link example with point obstacles. So the obstacle will be point obstacles and the robot will be for link robot. If you select choice number 2, to link robot that gets stuck in a local minima and must do a random walk to escape. So this is a different mode, and this robot will stuck in the local minima. You will see that it will not reach the goal location or the global minima. If you select choice 3, this local minimum is very deep, requiring a long random walk to escape. It doesn't always escape. Sometimes it is stuck forever. So if the local minima is very deep, okay, so random walk is something, a useful function to help the robot to escape from the local minima. Okay, so if it's stuck in very deep local minima, then this function will also not help. For choice number 4, you have the polygonal obstacles does hit a local minimum, but usually escapes quickly. So here your obstacles are not the point obstacles, but they have some shape. And if you select choice number 5, you get a 4-link robot. Polygonal obstacles has chatter that makes it take time to settle. So we shall try all these 5 choices, and the code, I think it's quite long, and because of these 5 different choices, the code is a little bit also complex, because the choices, it has different modes. And so what we gonna do is we have seen the previous code for the mobile robot and how it works. So let's try to make the choice 1 and run this code here. But first we have to type here clear all, and now just run. Change folder, and you see that this blue color is a robotic arm. This green color line is the desired location of your robotic arm. So you want your robotic arm, which is actually blue one, you wanted it to move to this location, green location. These small points, they are the obstacles, and they have a repulsive force within this red or the pink circles. So obstacle 1 has a repulsive force here, obstacle 2 has a repulsive force here, and this blue circle is your attractive force potential. And yeah, it finished very quickly. Let's try to run it once again and see how it works. See, the robot started from here and it tried to reach this green position, and this robot has 5 links. So yeah, the iterations I have put it 500, so let's make it 1000 maybe. Okay, let's see with control find and iteration. Yes, so here we found it. So here the iterations are 500, and now let's give it 1000, and let's try one more time here. So the robot, your robotic arm, is trying to reach this location, the goal location. As you can see, as the iterations increase, the error is decreasing. So now the robot have almost reached the goal location, but still there is some error of 0.23, which is acceptable. Okay, so now let's change the choice, and now we shall select choice number 2, in which we have 2-link robot that gets stuck in local minima and must do a random walk to escape. Here you have to put a value 2 and then press run. You see that here the robot started from here and it has reached the goal within 200 iterations. This is the 2-link robot only. So it started from somewhere here and then it got stuck somewhere here in the local minima, and then it needed a random walk or some kind of escape mechanism to escape this local minima, and then again it started to follow the low potential and finally reach the target. Let's see one more time. So here was local minima and then global minima. Now let's change the value to 3. In mode number 3, what we have is this local minimum is very deep. Okay, so this is difficult one. See that the robot gets stuck in the local minima here and it's not able to reach the goal, although you see that this green is the attractive force. The attractive force trying to bring it to the goal, but the local minima is very powerful or very deep, so the robot is not able to escape it. Okay, the reason is that here is an obstacle here. Okay, and because of this obstacle, the robot is being pushed away, and because of this goal location, in the meantime it is also being pulled toward the goal. Okay, so this is the reason why here this place is a local minima. This configuration is for a local minima, and you see that the robot failed to reach the goal location, which is this green line here, and it got stuck there. So even the random walk, the escape function was not able to help it out. So I think we need some more powerful function to get rid of this local minima. Okay, now let's see what is choice number 4. Choice number 4 is the polygonal obstacles does hit a local minima but usually escapes it. So now the obstacles are going to be have a different shapes, not only the points. Let's see how they look like. So this is the blue one is our robotic arm. It has 2 links, and it was stuck here in the local minima, and this was the goal. Green color is the goal configuration, and finally it reached the global minima or the goal location. So within 570 iterations. So you notice that it was previously stuck here somewhere. Okay, and then we need some kind of push or escape function to help it out, and finally reach the. So here the only thing is the obstacles are they have different shapes. Here the rectangular shape, triangular shape, and this pink color is a region where your repulsive potential is available. And yeah, let's try to run it one more time. Notice that this robot gets stuck here in the local minima, and now we need some kind of escape function to help it out. Otherwise it will always stay there. So now the function helped it, and it reached the goal location quickly. Finally, we see that now how the choice number 5 works. 4-link robot with polygonal obstacles. And now let's the choice as 5. So here this is the blue color is a robotic arm with 5 links, and this time you see it's taking more time because there are more number of links we have. So it's taking more time to reach the goal location. Yeah, so iteration finished. It doesn't accurately reach the goal location. There is some error, but this error is acceptable. Let's try to run it one more time here. See that here it is being pushed and being pulled by these 2 forces. And notice this magnitude, the magnitude of this force here. As it reaches near the goal, the magnitude of the force become less and less. So this is the end of this lab session. My recommendation is that you by yourself you try to run this code, try to change some values here, some parameters, and just try to run this code by yourself and have some idea that how changing these values or parameters affect the output of the potential fields. And you can try for mobile robot and also as well as for the robotic manipulator or the robotic arm. So thank you very much and bye.